Welcome. Let's take a look at an example of modeling projectile motion in space. Note that the position function for a projectile in space is a vector-valued function that accounts for the horizontal movement of the projectile, so the x component, and accounts for the vertical movement or vertical position of the projectile in the y component of our vector-valued function. Now, in this formula, v naught represents the initial speed of the projectile. Theta represents the angle of elevation at which the projectile is launched, and h is the initial height from which the projectile is let go. So we've got a situation here, so we're going to go ahead and model this situation and answer a couple of questions about it. So we have a baseball that is hit from 2 feet above ground level. So this indicates an initial height, so h will end up being 2. Continuing on, at 120 feet per second. So I do have to recognize that that is a speed, and it is in fact an initial speed because it's hit at that velocity. So our initial velocity is 120 feet per second. And then we have it being hit at an angle of 30 degrees, and that is with respect to the horizontal. So theta is going to be 30 degrees. So what we're going to do is we're going to go ahead and substitute those details into our vector-valued function and simplify any of the numerical quantities. So our vector-valued function r of t is going to be a vector with 120 cosine 30 degrees times t as our x component, and 2 plus 120 sine of 30 degrees t minus 1/2. Now we need to use an appropriate constant g for gravity. This is being expressed in feet per second, and so that constant of gravity is when we're dealing with feet per second, is 32 feet per second times t squared. Now notice that we will simplify cosine of 30 degrees. That's square root 3 over 2. And we will simplify sine of 30 degrees. That is 1/2. And we will also simplify the 1/2 times 32. So when we do that, r of t becomes, now the 2 in the denominator of the square root 3 over 2 in our x component can simplify with 120. 2 goes into 120 60 times. So I'm going to end up with 60 times the square root of 3 times t. And then my y component is going to be 2 plus, now in my y component I have 120 times 1/2, that's 60 times t. And then we have minus 1/2 times 32. 1/2 times 32 is 16. So that's going to be a minus 16 t squared. So there's the position function for this particular baseball, and the x component describes the horizontal position of the baseball, and the y component describes the vertical position. So looking at part B of this problem, when does the ball achieve its maximum height? And what is its maximum height? So when is a cue for me to find a value t So find t where maximum height. So keyword here is height. Height is a vertical distance. So we'll be looking at the part of our vector valued function that accounts for the vertical position of the baseball. So this function, this y of t, describes the vertical position of the baseball. So we want to find t where y of t has a maximum, because we want a maximum height. And then once we have that, then we want to evaluate y of t at that t value. Okay, so y of t, we want that to have a maximum. So y of t equals negative 16t squared plus 60t plus 2. So our derivative is y prime of t is negative 32t plus 60. So remember, using calculus, if we want to find where y of t has a maximum, we have to first find the derivative. And once we have the derivative, we look for critical points, and then we test those critical points. So now let's go ahead and search for critical points. So we'll say y prime of t equals 0 when negative 32t plus 60 equals 0. Let's add 32t to both sides of this equation. So 60 equals 32t. And then let's go ahead and divide by 32. And then we will simplify that. So the right-hand side is simpler to simplify. 32 divided by 32 is easy. It's 1. On the left-hand side, 15 times 4 is equal to 60, and 8 times 4 is equal to 32. So we're going to divide both the numerator and the denominator by 4. And when we do that, we get 15/8. So we now have a critical point. So t equal to 15/8 seconds is a critical point. We have not yet confirmed that it is a maximum. We need to test that. I'm going to use the second derivative test to confirm the maximum. And so if we do that, y double prime of t is equal to negative 32. And then if I evaluate that function at 15/8, that's still negative 32, which is a negative value, which implies that there is a relative maximum at that value of t. So at this point, we have the location of our maximum value, and now we need to just determine the maximum height. So to determine the maximum height, we will go ahead and evaluate our function y at 15/8. So we get negative 16 times 15/8 squared plus 60 times 15/8 plus 2. And so this becomes 58.25. So with the maximum height being 58.25 feet and the time being 15/8 seconds, we can say the ball achieves its maximum height of 58.25 feet after 15/8 or 1.875 seconds. Now let's consider a second question about this baseball. So will the baseball clear a 10-foot fence that is 300 feet from home plate? If so, by what distance? So this is asking if the ball will go over a 10-foot fence. That is the height of the ball greater than 10 feet, 300 feet from home plate? If so, by how much? So let's rephrase this a little bit differently. So when my horizontal distance, that's x, so when x of t equals 300 feet, is y of t greater than 10? If it is, then the ball will clear the fence, and we can find out by how much. If y of t is not greater than 10, then it will not clear the fence. So let's go ahead and start by finding out when is x of t equal to 300. Well, that's when 60 times square root of 3t equals 300. So we can divide both sides of this equation by 60 square roots of 3. So we have 300 divided by 60 times square root of 3. We can divide both the numerator and the denominator by 60. 60 divided by 60 is 1. 300 divided by 60 is 5. So this is 5 over square root of 3 seconds. So that's the time at which the ball has gone 300 feet horizontally. And now what we want to know is, at that time, is y bigger than 10? So now we want to consider, is y at 5 over square root of 3 greater than 10? So evaluating our function here, our y, at 5 over square root of 3, we get negative 16 times 5 over square root of 3 squared, plus 60 times 5 over square root of 3 plus 2. So that's negative 16 over 25 thirds plus 300 over square root of 3 plus 2. So if we combine like terms, this negative 16 times 25 thirds and the 2, we get negative 394 over 3 plus 100 times square root of 3. Now, because of this 100 square root of 3, it's not necessarily easy to estimate whether or not this ball cleared the fence. So let's go ahead and approximate that value. And if I approximate that value, I get approximately 41.87. And my units for my vertical distance, my y component, is feet. Okay, so when the ball is 300 feet away from home plate, will it clear this 10-foot fence? Well, the fence is only 10 feet tall, and notice that the ball will still be almost 42 feet in the air when it gets to the fence. So we can say that this ball will clear the fence by approximately the 41.87 feet that it is in the air minus the 10-foot height of the fence. So there will be approximately 31.87 feet between the top of the fence and the location of the ball as it flies over the fence. I hope you find this helpful.